Hi, everyone. My name is Adrian Cantu. I'm a PhD student in Dr. Rob Edwards' bioinformatics lab. I'm here to talk about cystic fibrosis. Cystic fibrosis is an autosomal recessive disease that causes secretion to become thicker. This affects mainly the lungs, where the increased mucus causes it to be colonized by microbes. Life expectancy for this patient is between 42 and 50 years, and 80% of patients die due to lung complications. So each patient presents a distinct microbial community in the lung that change throughout their lives. And changes in this community co-occur with what is called pulmonary exacerbation, which are periods of bad health and rapid disease in lung function. If you want to know more about the techniques and software we developed to characterize the microbes and viruses in these lungs, and to be able to do it in less than 48 hours, please come to poster number 3.
My name is Chris Leonard, and in our poster I will be presenting the concept and framework of our planned research. In this research we aim to develop a spatial impact statistic, abbreviated by SI, that will quantify a spatial unit's impact on an outcome measure within a time-varying geospatial system. SI will be sensitive to multiple scales of heterogeneity and will capture the spatially explicit structure and magnitude of a spatial unit's impact over a wide range of spatial and temporal scales. Exact SI will be calculated using the virtual environment of Searscape, an existing spatially explicit agent-based model with broad, high-resolution spatial coverage. From Searscape, exact SI and outputs from distinct sources of spatial dependence will be used to inform the development of a machine learning tool capable of estimating SI and other geospatial systems. At the conclusion of this research, the mathematical development of SI and the machine learning tool will be made publicly available. Please see me at poster 10 to learn more. Thank you.
Everyone, my name is Afruz. I'm a computational PhD student working in brain imaging lab. My research mainly focused on finding brain biomarkers using resting state functional MRI in autism. As you know, the prevalence rate of autism is 1 in 68. My presented research, I talked about the whole brain connectome association with behavioral measures. So as a result, I found cluster of voxels which can differentiate between typically developmental kids and autism spectrum disorder. So please come and visit me at poster number 13. Thank you.
Hello everybody, my name is Joshua Beamer. I'm a PhD student in computational statistics. My research and paper focused on assessing student success and retention under course intervention strategies. And we did this by developing an ensemble learning approach that allowed us to look at individualized treatment effects. And these treatment effects let us look at the success of the intervention, at-risk subgroups, and the effect of the intervention on individual students. And the main result we found was that students enrolling in this intervention tended to do better on their overall final exam score and their course grade in the course. And I'll be at poster 26.
Hi, my name is Stephanie Lauber. I'm a computational science PhD student working in the physics department. I'm here to tell you a little bit about my work. So many-body calculations allow us to determine nuclear properties, even for nuclei that are well beyond experimental reach, through the use of interactions either fit to data or derived from theory. The problem is trying to do a comparison of these interactions by parameter by parameter doesn't really make a lot of sense and doesn't let us determine any of the underlying physics. So the number of parameters in a given set will vary based on the interaction that you're working on. And in this project, we aim to characterize those interactions based on the most important linear combinations of the parameters. So using perturbative sensitivity analysis from nuclei ranging from neon 20 to argon 36, we were able to calculate a gold standard that we then compare other available interactions in our model space to. So if you'd like to hear a little bit more, my poster is number 23.
Hello, my name is Jordan Fox. My research is about ab initio calculations of gamma color transition strengths. So here are the 4 pillars of my research. First of all, I'm interested in nuclear structure. That means starting with the Schrodinger equation in this form, we solve for using a nuclear shell model basis. From these wave functions, I can compute observables like binding energy of nuclei, or in this case, radioactive decay rates. Now, we work in a no-core shell model basis using interactions derived from quantum chromodynamics. These ab initio interactions provide a much more robust model. However, they can be much more computationally intensive also. So pictured here is the supercomputer Edison that we use regularly for large-scale parallel computing. And finally, this framework allows me to tackle fundamental problems in nuclear structure physics. My current research looks at systematic bunching of gamma-teller beta decays. Thank you.
Hello, my name is Ryan Spakowski. I'm a second year PhD student here at CSRC. So my research is actually in nuclear structure. We want to understand sort of how matter behaves. And that involves my research solving the many-body Schrodinger equation problem. And when you do that, you get a vast amount of numerical information. And one of the treatments of that numerical information is you can decompose wave functions by group symmetries. So similar to signal processing, you can take some input signal, apply a transformation such as fast forward transform to break it up into individual components and examine these components. I do something very similar with beryllium isotope wave functions. And if you're interested in learning a little more about sort of what these kind of patterns you can see mean, come down to poster 1.
Hello everyone, my name is Priscilla Kelly and my research focuses on material science. In particular, we study how ultra-short pulse propagation goes through unique materials that have a zero or near zero optical response. So we have stacked layers of aluminum zinc oxide and zinc oxide, which have been shown to confine light to sub-wavelength sizes and have low losses. This allows us to create devices that are both smaller and faster. And if we use ultra-short propagation, we can look into applications such as broadband communication and super resolution imaging. If you're interested in our unique and dynamic material, please come see me at poster 4. Thank you.
Hi, my name is Matthew Portman. I'm a first-year computational science PhD student, and I work on superdense compact stars. We basically look at the matter inside the compact stars, and the goal is to simulate these stars and eventually use them as superdense particle laboratories. So the work that I will be doing is on implementing differential rotation in these compact objects, more specifically proto-neutron stars, so that we may better create a simulation to understand, I guess, the evolution of these into neutron stars throughout their lifetime. Currently working on that, and the extension of this would perhaps be extending it to gravitational waves or even larger objects. You can find me at poster 8. Thank you very much.
Hello, my name is Abraham Flores. I'm a first-year PhD student in the Computational Science program, working with Dr. Kenneth Nolan. I'm presenting today neutron scattering from Tritium using variational quantum Monte Carlo techniques. This is the foundational basis that I'm going to build off of here at SDSU. And my roadmap looks like taking this in single channels into multiple channels, which is where the scattering collision rearranges protons and neutrons. That currently has not been done yet with quantum Monte Carlo. And then so we'll be making use of Green's function Monte Carlo and optimizing our parameters. You can find me at poster number 28. Thank you.
Hello, my name is Wen Pan, and I'm a PhD student in computational science. This project is about indexing data structure for DRAM and persistent memory high resistance, and the critical data is stored on persistent memory. The reconstructor of data is stored on DRAM to help the performance, and the reconstructed data is always can be reconstructed from the persistent data in the persistent memory, and we also use enhanced memory allocator to help the performance. If you're interested, please visit the poster 27.
Hello, my name is Parsing. I'm a 4th year PhD student at Multimedia and Wireless Network Research Group, and there's the supervision of Professor Sanil Kumar. My research is focusing around the frequency division duplex nodes in multi-hop scenarios, and we are looking at the channel selection problems, and we are using graph theory techniques to model our problems into the graphs, and we introduced a novel bipartite graph coloring scheme that is only using distributed informations and clustering to do the channel assignments on these type of networks. So if you're interested in more details, come and visit me in poster number 29. Thank you.
Hello everyone, my name is Shuan He, a PhD student at the CSRC, and I work with my advisor, Professor Wei Wang. Our research area is wireless network. In this poster, we are facing the problem that how to improve the profit of content provider and wireless carrier, and also we want to improve the quality of experience of the mobile users. In our work, we leverage the smart media pricing concept in our work, and we proposed a generalized best response game theoretic solution. By acquiring the equilibrium state, we can reach the we can obtain the optimal data consumed by mobile user, and we will get the optimal price that's charged by the CP and WC. If you are interested in our work, please visit me at the poster 17. Thank you.
Hi, good afternoon, everybody. I'm Kevin Joyner, a PhD student in computational science and a member of the Lupi Lab. Studying bacteria and viruses in the environment is experimentally challenging. So for my research, I've developed an agent rule-based model which simulates bacteria and viruses using lifestyle parameters inputted into the system. Through our partnership with the Bioinformation Institute, we're able to calibrate our model, which is providing realistic simulations, which is revealing interesting interactions, relationships, how the virus's interaction with the environment influences its ability to infect bacteria and proliferate throughout the colony. So if you want to hear more, come see me, poster number 16. Thanks.
I'm part of the Lupi Lab, and therefore I also study bacteriophages, which are viruses that prey on bacteria. Like bacteria, they're found everywhere in the environment, from the gut to the ocean. And what we are trying to do is try and find out what the bacteriophages can tell us about the environment they're found in. Currently, the approach that we're working on has to do with machine learning techniques to find out whether the major capsid proteins on the shell of the bacteriophage can tell us anything about the environment they're in, because we know that their lifestyle is affected by the environment. Those major capsid proteins are made up of regular DNA building blocks, but in specific orders, and so we're using currently random forest techniques as well as ensemble voting methods to find out whether they can tell us anything interesting. So if you're interested in bacteriophages, in machine learning, or craft beer, please come talk to me at poster number 24.
Hi, my name is Misha Kutzman, and I'm a first-year PhD student in CSRC, working in the math department with Professor Jerome Gilles. Epilepsy affects about 3.4 million people in the US alone and is characterized by spontaneous recurrent seizures. Treatment options include surgery and long-term medication, which can lose efficacy over time if the body develops tolerance to it. So seizure detection and prediction schemes use EEG data, as you can see up here, in the hopes of providing early notification of the onset of seizure events so that the patient can either take medication only when necessary to avoid tolerance or to move to a safe place before the seizure occurs. Various signal processing techniques are used to denoise and extract spectral feature information from the EEG signal, which is then fed to a machine learning classifier that can distinguish between seizure and non-seizure time windows. In poster number 5, I will be discussing how this process can be improved by creating a patient-specific method for extracting spectral feature information, thereby sharpening the performance of current schemes and potentially improving the lives of a wider segment of the epileptic population. Thank you.
Good afternoon, everyone. My name is Kansham, and I'm working with Dr. Satish Sharma on high-gain beam steering antennas for satellite communication. So we have developed a new radiating element which we call as butterfly antenna. This antenna is inspired from the symmetric shape of butterfly wings. This novel antenna can be used for beam steering and provide excellent scan performance compared to other circular polarized antenna. The proposed antenna is designed using finite element method in high-frequency structure simulator, and is also fabricated with the integrated feed network beamforming complete network, and is currently being measured here in the mini-compact range at San Diego State University. If you would like to know more about this project, please visit me at poster number 6. Thank you.
Hello everyone, my name is Bunli, and I'm working with Professor Nguyen, and my work is about learning methods for mode light detection and using low resolution ADC. So the picture here is that the demand for data transmission is increasing very fast. So as you can see here, for example, the mobile data traffic is forecasted. It is increasing very fast. So future networks aim to provide high data rates. So one solution is to use multiple transmit antenna and multiple receive antennas. And another solution is to use higher frequency to transmit signal. And one problem is the power consumption. So the solution to deal with the problem of power consumption is to use just a few bit resolution of the ADC, the analog to digital converters. So what I'm considering here is to perform the data detection without the knowledge of the channel. So if you are interested, you can see me at the poster number 7.
Good afternoon, my name is James Molinix and I'm a PhD student at Computational Science Research Center working with Professor Luque. So what I'm here to talk about today is fractal analysis, in particular the box counting algorithm. Now, rather than go on a diatribe about such complex topics, I'll just talk about an example. On the poster there is level 1, a square with a hole in it. Now, most reasonable people would say that that's a two-dimensional object. After applying box counting, however, and applying some statistics, level 1 yields us a 95% confidence interval does not include 2, which would suggest maybe it's not two-dimensional. Well, that doesn't really make much sense. To hear more about how we address that issue and try and bridge that gap and learn how we just tweak the knobs of box counting and include information that's otherwise discarded in the process, please come see me at poster 11. Thank you.
Hello everyone, I'm Harish Natarajan, a fourth-year PhD student at CSRC. I work under Dr. Gustav Jacobs of the Aerospace Engineering Department, and my research topic is CFD simulation of chemically reactive turbulent flows, where the small-scale motions and the chemical reactions are modeled using probabilistic methods. So this mainly involves solving of transport equation of some stochastic particles. Typically, these are solved using Lagrangian Monte Carlo methods, but when combined with the spectral element methods, tracking of the particles becomes complex and challenging. So we develop a novel semi-Lagrangian method where the particles remain on the grid points at all time steps. This makes this method local and highly parallel. To know more details about the method, visit me at poster number 14.
Hello everyone, my name is Luis Escalona and I am working in damage identification in carbon fiber reinforced polymer materials, which are materials used in aerospace industry. The goal of my project is to use an imaging technique known as electrical resistance tomography. But using this technique in this kind of materials is very challenging, especially when if we want to identify internal damage known as lamination. So today I will present how to overcome the problem that is basically related to the large number of sensing combinations if you want to use electrical resistance tomography for damage identification. So if you are interested in more about my topic, come and visit me in poster number 19.
Hi everyone, I'm Robert Inslee, and I work with Chris Curtis on vortex methods. So what we do, well, the purpose of our research is to explore the relationship between underwater vortices and surface waves in shallow water. So to do that, we use a very fast method that puts it in terms of the vortex and surface variables alone. And, well, vortices in nature aren't at one point. They are spread out over a volume. So to approximate that, we use a closely spaced grid of point vortices. If you want to learn more, come visit me at poster 20.
I am Esteban Vasquez Hidalgo. I work with Dr. Carlo. Calcium is a necessary ion in heart contraction. At the cellular level, calcium enters the cell from the extracellular space and diffuses across the cytosol reaching ESR and intercellular calcium store. This extracellular calcium activates the ryanodine receptor, which releases SR calcium, creating a sudden increase in cytosolic calcium. This increase in calcium triggers contraction. After contraction ends, calcium is removed to the SR by the circuit pump or excluded via the NCX channel. Proper handling of calcium is essential to maintain function of the heart. Our research investigates how downregulation of key proteins affects calcium signals. We use mathematical models to predict expected calcium response and better understand molecular and physiological mechanisms in heart health. For more information, come see me at poster 22.
Hi, my name is Eric Medvedev, first year PhD computational science student working with Tristan Hillis, first year master's student in the computational science department. We're working with our advisor, Dr. Jabba Eliel, in the field of applied computer vision and machine learning. Our project is on detecting multiple objects from traffic cam footage, in general, vehicles and pedestrians. And what we're doing for the future is synthesizing and augmenting additional samples to add more information to our training set, and then develop a knowledge base and a knowledge reasoner to start learning in a long-term context. Thank you.
My name is Lisha. My advisor is Dr. Yu. I'm the PhD student of computational statistics. The crossover trial is very appealing in clinical trial designs because it can often improve the efficiency of the parallel group design and other common design with repeat measurements. The important feature of crossover design is using the washout period, which clear out the carryover effects. But however, in the reality, carryover effect is very hard to avoid. My research is about how carryover impact efficiency of the crossover design. If you want to know more, please come to poster number 2.
Hi there, my name is Jared Brzezinski. I'm a master's student at the CSRC. My poster is on my project I did for Comp 670, which is effectively a 1D equation, 1D wave with large CFL values. Basically what I did was, starting with a smoothish square wave, I vectored it twice across the domain, keeping the space and time discretization the same, and using second and fourth order mimetic divergence and gradient operators, they see how fast can I push it before it explodes. The results are super interesting. If you want to come see me at poster number 12, I'll tell you the answer. Don't look at the board.
Hello everyone, my name is Santi Boada, PhD student at the CSRC, and in this research we basically examine the viability of high-order mimetic operators, gradient divergence curve, on overlapping grids, which are very useful when solving problems that involve complex geometry or moving particles. So for this reason, we show numerical examples that illustrate the effectiveness of our method, which include the anisotropy on elliptical problem, which is basically a full tensor. For more information, please consult me at poster number 9. Thank you.
Hi everyone, my name is Sydney Arkofer and I'm a first year PhD student. I work under Dr. Castillo doing coastal ocean modeling. The research group that we both belong to is currently developing a general curvilinear coastal ocean model known as GCCOM. With my group, I am using this to simulate internal waves traveling through La Jolla Submarine Canyon. Submarine canyons are just underwater canyons that jut into the coastal shelf. I'd love to tell you all more about what I've been able to learn about submarine canyons. So please join me at poster number 8.
Hello everyone, my name is Manuel Valera. I'm a third-year student here at the CSRC and PhD program, and my project is about MPI CUDA acceleration of the PETSI parallel fully 3D curvilinear non-hydrostatic coastal ocean dynamics model, GCCOM. So the GCCOM is ultra high resolution. It has recently been validated for experiments. So the last step before being a world-class leading-edge model is just to make it speedier. We have to speed it up into manageable times. So for this, during the last year, we have been developing the model into an MPI framework based on the PETSI libraries, and we found out that some parts of the model are not parallelizable. For this, we are employing now NVIDIA Volta GPUs, and currently we are able to speed up what used to take us a month of work into 1 day of computational time. If you want to know more, come see me at poster number 25.